Hey everybody, welcome to Techforpsych. I'm your medical doctor confidant, Dr. Cody Rall. I know a lot of you are interested in the Muse Headband, and we want to take a look at individual sensors today on the Muse Headband to make sure that the EEG signal is the highest quality that you deserve in your own practices with the Muse Headband, whether that be doing neuroscience research, meditative exercises, taking a look at your own brainwaves on MindMonitor. These are really important things that you can be doing with your time, so we want to make sure that the EEG signal coming out of these sensors is of the highest quality. So I wanted to bring on neuroscientist Kiefer O'Sullivan onto Techforpsych today to talk to us about his process and taking a look at raw EEG signal and processing it to determine the quality of that EEG signal. And Kiefer is going to show us some really interesting findings that he's found over the years between the Muse 1, Muse 2, and the Muse S. So stick around.
What I do with Muse is taking some of the raw data out, and so what I do as an in-between for that is I actually use the program or the app MindMonitor, right? So MindMonitor is a great in-between. When Muse kind of took out their Muse Direct option, we kind of were left with very few options for getting the raw signal out of the Muse device. So one of the options, if you're a researcher or just a biohacker, is to get the MindMonitor app. Go into the settings for that, and you'll find a setting for recording interval, right? The recording interval is usually set to 1 second, so that's basically like the app is basically sampling the data stream 1 time per second, and then that's what you're seeing displayed. So for neuroscientific purposes and research, we typically like around a sampling rate of around like 256 hertz maybe, or 500 hertz, or upwards and downwards of that depending upon what you're interested in studying. But the Muse hardware actually has a native sampling rate of 256 hertz, where you're actually able, by setting MindMonitor to constant, instead of sampling at once per second, it'll sample that data stream 256 times per second. So the resulting CSV file is usually like pretty big depending upon how long your session is. But you can basically get that from MindMonitor, upload it to Dropbox or something like that. So you then have that raw CSV file. And then that's what we want as researchers, right? That's the kind of thing that MindMonitor is the workaround to get us to this raw data stream. And so once you have that raw data stream sampled 256 times per second, you can then, find your EEG program of choice. EEG Lab is a great one. I use Brainstorm primarily, which is very, very similar to EEG Lab. It actually uses a lot of the same code, but it has a lot of additional features that you can use as well, which is nice for me. And so from that, you can basically get the raw stream from Muse and then port that into, the neuroscientific analysis program, whatever it is you're using. And then from there, you can do, whatever's in your pipeline to do. So for me, I like to do a lot of different cleaning, applying filters. One of the biggest things I found for me is ICA, which is independent component analysis. So with independent component analysis, it basically looks at the signal and finds sources of like recurring artifacts. So if there's, a particular type of eye movement or a blink or a source of electrical noise that is really interfering with your signal, it can find that and identify it for you. And then you can get the option to kind of, do I want to remove all of this from the signal? And so with that, you get your raw data stream. It's now in that app, or it's now in that neuroscientific analysis pipeline. And then it's a process of almost kind of whittling away all the other activity until you get to that golden kernel at the center, which is basically the brain data. And we have to do that because, as you can imagine, right, we're wearing this EEG, headband, on the outside of our skull. And we're interested in hearing what the brain has to say within the skull. But unfortunately, the skin and the muscles and all of the different physiological components in between the headband and the brain all also have things to say. And so we kind of have to silence them in various ways to actually just get to what is the brain really, really saying, and, doing a really, high resolution analysis on that. So for your files, you sent me some files between your Muse 2 and your Muse S. So for those two files, I left them relatively unfiltered, right? Just so we could see what are these devices natively outputting if I didn't clean it up or touch it up or do anything like that. And so one of the biggest differences you can see that's pretty apparent is on the Muse 2 graph, you can see that there's the green and the red line, right? Basically one for the frontal electrode and then one for a temporal electrode. And on Muse 2, you can see that it almost looks like two different signal types or signal sources. It's one kind of looks like a more typical EEG, the frontal one does. And then the temporal almost looks like maybe even more of an EMG or just something that has some kind of noise in it that is not, brain related. And you can kind of tell that generally by that, much wider spectrum of activity. Brain activity is so fine. It's typically, to put a number on it, it's typically between like maybe 5 and 20 microvolts. And then on the temporal sensor, you can kind of see how things expand kind of past that. And so that's a quick visual way when looking at a signal to go, oh, something's weird here. If I did an analysis on this, it would come with a certain output, but I wouldn't have a lot of confidence that that output represented 100% of what the brain was representing. So this is in contrast somewhat when you look at the Muse S. So I did the equivalent time equivalent analysis on the Muse S, and you can see the comparison between the temporal and the frontal electrodes there, and they're actually very, very similar. And so from there, you could actually see how it'd be very, very hard to tell the difference just visually between the frontal and the temporal on that side, because they both just look like pretty reasonable EEG, raw spectrograms, right, or raw graphs. And so from that perspective, it's really interesting, the differences between the two devices. And that's a big key for me as a researcher in terms of really wanting access to those temporal sensors and wanting to get really good data from them. And so that's, the decision between a Muse 2 and a Muse S, I think is kind of a complicated one. And it really depends upon who you are, what you want, and what you have already. I think for me, if cost isn't an option and you're a neuroscientist and you want the latest Muse device that has the greatest ability of getting brain data from all four sensors, it's pretty apparent that the Muse S offers that over the Muse 2.
And so we were talking about the signal quality, and I think that you had mentioned that there's other unique aspects of that as well. You can take a look at the data and see that it's better, but it's for a couple of different reasons, right? It's hugging your head. There's a difference in sensor size. Would you mind talking about that a little bit?
Yeah, 100%, because the fit especially is a huge factor when it comes to EEG. So for those people that have had an EEG done at a hospital or a neurofeedback lab or whatever it is, and you've worn that cap, right? We all kind of know that cap is tight. Like when they put that thing on, it's really hugging your skin tight. And it's really hugging the electrodes consequently in tight. And that's actually for very key reasons, because you want the electrodes to be contacting the scalp in the same position at all times, right? And you don't want them to move very much. So if somebody's shifting left or right, or they're tensing their jaw, or moving their eyebrows up and down, or their eyes, that can tend to maybe shift the scalp, shift the skin a little bit, and all those micro movements between the electrode and the skin will play havoc with the signal. So when if you're in an EEG lab and you're sitting in front of somebody and they've got the cap on, and they just touch one of the electrodes, or they move it a little bit, and you're watching the screen, your whole electrode sequence just goes haywire until they stop, and then it resets and gets going again. And so that was one of the really nice parts of the Muse S, is that you can actually attach it pretty tightly, which is kind of, for me, a much better way to wear an EEG device. With the Muse 1 and Muse 2, it is very nice to just, throw it over the ears and that's that. But with that ease of wear comes also the ease of movement that does cloud the signal a lot. And so you can imagine, every time we move, anytime something with your jaw, your tongue, these little muscles around the back of your skull and your ear also move, and that kind of shifts the device. Anytime you move something on your forehead, that might shift the device a little bit as well. And so it may seem very minute to the average user, those types of little things, but when you're really wanting a very clean EEG graph, those types of things really matter. And so that's another thing that I really enjoy about the Muse S. And especially as well,
I know you had an opinion a little bit on like the nature of the actual rubber electrode sensors as well on the first two.
Yeah, that's actually a huge point as well, because the electrode composition on the Muse 1 and 2 between the frontal and the temporal, the side electrodes, are actually different, right? It's actually two different types of electrodes that they're using to get the signal. And that's partially why, when you look at the raw graph on a Muse 1 or the Muse 2, you can see you can see that it's almost like two different heads, two different brains, two different sources of signal. And that's a huge thing for the Muse S, is that the frontal and the temporal electrodes are actually made of the same stuff. So whatever they're getting a very similar type of flow through, let's say, compared to the conductive silicone ears of the Muse 1 and 2, which fit very well, but get so much noise that it's often kind of useless, quite frankly. I actually was running an experiment recently on remote Reiki practitioners, and I was using the Muse 1, and I got all the data back and was going through it all. And as a scientist, as much as it was like a huge pain in the butt, I was like, I just kind of have to throw out these temporal electrode, that entire data block, right, from the temporals, because the way it looks on the data, it just looks like a bad channel, right? It just kind of looks like, when you're working in EEG lab, you have very strict standards of, okay, I'm going to put all these channels on and they all have to fit a certain standard. And if certain channels do not fit a certain standard, then they just kind of get classified as bad data, because you can't count on them to be reporting brain data accurately. So you're not really sure where this data is coming from. And so you're kind of forced to just toss it aside. And so that was a huge bummer for me on the research side of using the conductive silicone, older hardware, is that I had to cast that aside. And so if I was using a Muse S, I would have much greater ability to use all 4 electrodes and get, very similar data streams from all 4 electrode types.
So the electrodes are more similar, there's a better fit. And I think that there was some nuances in terms of like the electrode size on the Muse S that you were talking about as well.
Yeah. So that's a big factor as well. And so we can look at, I've got my Muse S here, and so you can see that they're pretty broad electrodes for what an EEG is, right? When you compare that to Muse 1 and 2, there's a little bit different surface area, right? I think the 2 and the S are closer in terms of surface area. I know the 2 also has a little bit broader. I know the 2 also kind of has them horizontally, and then the S kind of has them vertically oriented. And that's kind of compared to the 1, right, which had much more discrete kind of sensors. And so for people that are using MindMonitor, right, and not going and doing the data analysis in the Brainstorm or EEG Lab and stuff like that, they might get stuck with a lot more EMG in their graph. So EMG is basically electromyograph, right? So it's a measure of muscles. And so an EMG is very, very similar to an EEG. It's just basically the same process of, getting an electrode, attaching it to the skin, and reading the muscular activity that comes from the electrical activity that those muscles produce. EMG electrodes and EEG electrodes typically differ primarily in that size, right? So you can imagine when you want to measure a muscle, you take that electrode and you make it larger to get that greater, noise, maybe across a forearm or something like that. And then EEG, we want very discrete electrodes at very specific sites, and then we do calculations kind of based upon that. When you take, something like the Muse 2 and the Muse S, and when they have their larger electrode surface area, that just allows more of that EEG or more of that EMG signal to come through. So you can imagine that it's almost like it has the capability of hearing a louder volume of the muscles compared to the more very quiet kind of chatter of the brain, right? And so that can be something to watch out for, because if you're used to using MindMonitor and getting certain results, and all of a sudden you're using a new device and there's more EMG speaking out through those results, your results are potentially getting clouded by that. And so typically you'll see that for EMG, on the forehead, you'll see that in typically two different ways. For like tension-based stuff, so maybe like a wincing or somebody furrowing their brows, something like that. That's typically like a beta gamma type of artifact, to where that continuous that continuous activation of the muscles is a kind of a high frequency type of artifact. And then on the flip side, you will see the movement of the eyeballs and also just eyelids and muscles and things, those discrete kind of individualized movements in the lower frequency. So they would kind of bloat up your delta and sometimes your theta values as well. And so that's something to be mindful of with some of this newer hardware. If it, when you're seeing the electrode sizes kind of get bigger, it should kind of key something in your brain to be like, okay, there might be more EMG represented on this than EEG compared to what I'm used to.
Yeah, and we covered all the technical things, but what would you say your opinion is on like level of comfort and how that plays into your choice between Muse 2 and Muse S? Yeah,
for me, I like the Muse S better comfort-wise. For me, I tend to not notice it. Even though it's a little bit tighter, right, I tend not to notice it as much when I'm wearing it. I also enjoy on the fit and the comfort side of Muse S, I actually get to wear it like a little bit higher on my forehead, right? So that's one of the interesting things as well, is that, Muse, its frontal electrodes are technically AF7 and AF8, right? That's what they're listed as. But typically, they're almost always worn in the FP1 and FP2 position, which is right above the eyes, right? And so that's where the headbands typically sit, and then you don't have much ability on the Muse 1 or 2 to kind of alter that, compared to the Muse S, to where my electrodes actually sit, right above, kind of more flush with my hairline, which is much closer to actually the intended AF7, AF8. And so from that perspective, it's more comfortable, and also more comfortable in actually getting the electrodes that it's advertised and getting. And so for me, I think I tend to gravitate towards the S over the 2 in terms of just pure usability.
So I don't know about you, but I found that conversation with Kiefer very informative, very interesting. And as you can see, he's a wealth of knowledge when it comes to understanding EEG, especially when we are getting data in the wearable form. I mean, Kiefer is running neuroscience experiments through top-of-the-line software, so he needs high-quality EEG signals to make this work. And what he found is, as you heard him explain, is that those back rubber sensors on the Muse 1 and Muse 2 are very liable to artifacts. So if you are using those two for research, you have to make sure that you have them wetted, that they're fitted properly on the clients, and that there's not a lot of movement, or else you'll get EEG data that's really quite useless. And it's hard to compare the frontal sensors from the back rubber sensors in terms of being able to determine what exactly is going on in a neuroscience experiment. Now, I think that the higher line companies like Muse itself, in their software, with their algorithms, are able to get around the differences in data quality, because they're using machine learning on the EEG data, and hopefully they're able to figure out how to get some of those artifacts out in order to deliver you a good neurofeedback experience. And I know for a fact that the MindLift program is really a stickler on making sure that you've got good EEG connections between your scalp and the electrodes before you can even begin to engage in the neurofeedback experience and training processes. But for those of you that are using MindMonitor out there and running your own neuroscience, neurohacking experiments, it's hard to tell whether or not that signal is really high quality when you're just throwing the headband on and relying on the little horseshoe image and recording your own EEG data during different things like meditation. So hopefully this interview educated us all on what to watch out for when using these devices on yourself and with clients to gather data for our own experiments, and maybe gave us a little bit of hope of where this is headed, where the future wearables will take lessons learned from the iterations of the Muse in order to deliver us the highest quality EEG data possible so that everybody has the best data for their own experiments and we can move this field continually forward. Thanks so much for the listens. Dr. Cody Rall, that's all I had for today. Future videos that I have planned are a more comprehensive view of between Muse S and Muse 2 and what you should buy. There's some nuances there depending on what kind of research or work you want to do with the two. And then also a more in-depth look at the new Muse Sleep program, the software that they've introduced. The software will be able to track your sleep throughout the night. So that's very much worth taking a look at. See you next time.